So welcome back to the presentation 14 of our algebraic structures discussion. So in this one, in the last session, we discussed direct product of groups, and we did that just to help us with the classification of groups to some extent. Now let's go back to our discussion prior to that presentation 13, that is the presentation 12, where we talked about the left cosets and Lagrange's theorem. Okay, so let's go back to our group of integers with addition as the binary operation. And I am it just so happens that I am taking this group multiples of 6. All right, I could have taken multiples of 4, multiples of 3, or anything. I just decided to take multiples of 6, okay, which is also a cyclic group generated by 6 as well as by -6. And again, the operation is the addition of integers. Okay, so we have a group G and a subgroup H. And now remember this, we could form what you called the cosets of this subgroup H in G. And how did we form them? So the cosets that we are forming are the left cosets. And remember this, the left cosets will be of this type, XH, which will actually mean X plus H, where X is an element of G or integers in this case. So for instance, I added 0 to every element of this subgroup. So adding 0 means the same thing. So these are the multiples of 6. So this will be what? Just 0 mod 6, right? Likewise, if we go further, so if we add 1 to the subgroup, every element of subgroup H, which is looking like this, I'm adding 1. So what they will be, they will all be the numbers that are related to 1 mod 6. Likewise, the other cosets would be 2, 3, 4, and 5, their equivalence classes. And when you add 6, you again get multiples of 6, right? Which brings you back to the equivalence class of 0. Likewise, if you added 7, you start repeating yourself because now you are again adding 1 to multiples of 6, which is what? Which is just this cyclic subgroup. So you are back to 1. So what happens is all the cosets here would be 0, 1, 2, 3, 4, 5. And these guys, they form a group with respect to addition mod 6. Okay, so if we look at all the left cosets, they form a group with respect to addition modulo 6, and that 6 was related with this. So now let's go with this idea further for groups in general. So again, now we are taking a general situation that H is a subgroup of a group G, and we are taking all the left set of all the left cosets. For example, if you look at this, what this was the set of left cosets, okay, of the cyclic group generated by 6, right, of in Z, right? Okay, and we saw that this is a subgroup with respect to addition modulo 6. So what we would think of is, this was an example, and above we are talking. So what we want is, let's go back here and just try to see if we can give a group structure here in general on this subset of the group. No, it's not the subset of the group G, actually. It's just another set, okay? All right. So if we do that, then we may propose a binary operation like this, that XH, and say we have another element. Let me put that in parentheses just to distinguish them. So say we got XH, then we got YH. So for the binary operation, let's propose that this would be the binary operation. That is, if I take these, if I multiply these two sets, what it will mean is that it will mean that this is the following set, and I'm writing that in a hurry. I hope I don't make any like a, you know, thoughtless mistake. It's okay. So this is of this type, all right, where X, Y, they are in G, okay, and we are taking H1, H2, of course, they are in G, but specifically, they have to be in H, okay? All right. And this is just a typical left coset of H in H by XY. All right. Sorry about that stammer. Okay. So now let's see when will this be possible, or when we would be able to obtain such a binary operation structure in a valid manner. So question is, what did I mean in a valid manner? So let's go and do some calculations. So I brought our discussion to this marker board. That is, this is what we are wondering about, that would we have a group structure, you know, on this set, okay? So what we want to see is this a valid binary operation? And what you would need for that is, if you remember, if I have this condition, AH is BH, right? And say GH is, let me take UH, okay? So what should that mean is this, that AGH should be BUH to satisfy the condition that the operation defined by this is a valid binary operation, or in other words, it's a valid map. So remember this, that if you look at this condition, this means that A inverse B is H. Remember, that was actually the very relation that had created these left cosets as equivalence classes, right? And this guy will mean that G inverse U belongs to H, right? So we have these two things given, and what we have to do is, let's color coded this one differently. So we want to know, I hope this green color is visible, or let me take it like say blue. All right. So we want to see if this will be valid. In other words, we want to see if AG inverse BU, if that belongs to H, right? Okay. So what we have is, we have this, and so we got A inverse B as say H1, right? And we got G inverse, one moment, and we got G inverse, oh, it again came out to be in same color, okay? G inverse U, uh, yeah, this is say H1 and this is say H2. All right. And what we want to see is that if this guy will end up in H, and what do I mean by that? AG inverse BU. So let's go over these step by step. If I look at AG inverse, then you know AG inverse is G inverse A inverse, and using the associative property, because the multiplication among these is just inherited from G, so that is associative, right? So we got this element, right? Now here, pay attention to the middle. So you will get what? You will get G inverse, and then we get our H1 in the middle. Remember, that's what we are getting from here. And then what do we get? We get U, right? Okay. Now let's see who U will be. If you look at this portion here, then U is GH2. If we were sitting in a classroom, most of the times I'm able to get all these steps from the class participants, but unfortunately we don't have that opportunity. So I'm just going the way my head is dictating. Okay, so here U is what? GH2. So what happens is we get this element equals G inverse H1, and then U is what? GH2. All right. So now we got this portion here, right? So what we see is this. In case this is in H, what do I mean? In case G inverse H1G is in H, then then that element times H2, H being a subgroup, will be in H anyways, right? So what we are seeing is this, that here this will work out really nicely, okay, when if we have this kind of condition that G inverse HG, that is in H. All right. So now I'm just going to go ahead and borrow the proof and the ideas from our book to proceed further. So we have, if H is a subgroup of G such that G inverse HG, that belongs to H for every little g in capital G and for every small h in capital H, then we can have xh times yh, and of course where x and y, they are elements of G as a binary operation in the set of left cosets. Okay, and if you want, you can write this like this. If you want, that this simply is xh yh. All right, so this is a binary operation, and if we let's formally write for x y z in G, okay, I can write for x y z in G. Say we got this, that what we are doing is that we are just thinking of checking the, not thinking of, actually we are checking the associativity. So if we do this, what do we get? We get xy h, right, times zh. So that will be, if you go formally, well, xy z times h, that's what this will become. Now since the binary operation in Z is associative, I can interchange these, right? So we got X, Y, Z, and then H here, and then I can write this as XH, then what? Y, ZH, And so what we got then is this. Let's just take the value on the extreme left and bring this in here. So what we get is, I can write this value as YH times ZH, right? So this is also associative, right? Okay. And then for the identity, I mean, again, if we were discussing it in the class, I have never ever had a class in which somebody did not guess that if E is the identity in E, then EH, since E is in H, will be H, that is the identity. And again, uh, almost always people found that if I take XH, okay, then X inverse H is the inverse of the element, is the inverse of the element XH for any XH in this set. So what happens in this case? All these sets of, this set of left cosets, that just becomes a group with respect to that binary operation. And actually, what the book shows is this, and it does the proof very nicely, so I'm not going to repeat it for you, that if we have, let me just bring that from here, that if we have this, okay, then what will happen is this, that if you take GH, that is the left coset of H, or left coset by G of H, then that is the same as the coset multiplying obtained by multiplying this G on the right. So you will call this the right coset. So the book shows that very nicely, approves that very nicely, that this is equivalent to this, that this would be true for every G in G, that each left coset by any element G, okay, equals the right coset by the same element, and of course of H. Okay, so H has to be that kind of a subgroup. Okay, so of H and of H here as well. Okay, and when this is true, when this condition is true, then we say that H is a normal subgroup of G. Okay, so in brief, or let's just go ahead and summarize what we just did. Okay, that is, if we have this, and I'm rewriting the same thing, so forgive me for that. Okay, if GH equals HG for all G in G, okay, for the subgroup H, okay, we say that H is a normal subgroup of G. And what happens in this case? The set XH, okay, where X is in G, or this set of left cosets of H, okay, is a group, and that is called a factor group. Okay, and remember this, if you recall when we discussed the Lagrange's theorem, that if G is finite, of course, then H will be finite, then the order of this group was the order of G divided by the order of H. Okay, so it's called the factor group, and also it's denoted by, in a factor style, it's called a factor group, G, G by H of G, of course, the factor group by the subgroup H. Okay, so let's see that what kind of subgroups are normal, what kind of subgroups are not normal. Okay, and if you look at that, then, well, we have two criteria to check whether subgroup is normal or not. One is this, just check GH is HG or not, or another one is the a weaker condition that we took, that G inverse HG should be in H, all right, for all little g and big G, and H in H, and of course H is an element of G as well. H I meant. Okay, so notice this now, that if G is abelian, and again, you can check this condition or check this condition. Both of them will be a good test for a subgroup being a normal subgroup. Now, but if G is abelian, okay, that is, the operation is commutative, then what happens? This element will just be abelian, means I can just write this as HG is the same as GH, right? And G inverse G is the identity. Identity times H is H, and that will be in H, right? So if G is abelian, every subgroup is a normal subgroup of G, right? So every subgroup of G, of G, okay, is a normal subgroup of G, right? Okay, but the problem occurs when we have a non-abelian group, right? So for example, let's take our first non-abelian group that we encountered, that was the permutation group on 3 symbols, right? And if you recall the elements were, now instead of writing them by hand, let's not forget that we have, in addition to a free textbook, a free software also, that is the Sage Math. And here we can have it list the elements of S3, the symmetric group on 3 symbols, like this. Okay, so let's look at this, the elements of this group. For example, if we look at this element 2, 3, it's a transposition, and the order of 2, 3 is how much? It's simply 2, because if we look at 2, 3, who is 2, 3? That is this permutation. If you multiply it with itself, what it will give you is the identity permutation. So what happens is, you can take a group H as the identity element and the element 2, 3, okay? And now let's look at its, say, left coset with the element 1, 2, 3. So if we do that, what we shall get is, we shall get 1, 2, 3. 1, 2, 3 times the identity is 1, 2, 3. But when we take 1, 2, 3, which in fact is 1, 2, 3, 2, 3, 1, and 2, 3 is 3, 2. So let's look at this. Here 1 goes to 1, and so 1 goes to 1, 1 goes to 2, this goes to 2, 2 goes to 3, 3 to 1. We got a 1 here, and 3 to 2, 2 to 3. So this is 3. So simply it becomes what? It simply becomes this element, right? So this is left coset of H by this element. Now let's compute the right coset of H by this element. So first this element will show back up, right? Okay. And then if we multiply 2, 3, which is 2, 3, 3, 2, by this element on the right, what do we get? We get 1, 2, 3. So 1 goes to 2, 2 goes to 3. So we get a 3, 2 to 3, 3 to 2. So we get a 2, 3 to 1, and 3 to 1 and 1 to 1. So we get a 1. So this is 1, 3, 3, 1. So we get 1, 3. So what we notice here is that in this case, these guys are not equal, right? This left coset. So this subgroup that we are looking at is not a normal subgroup, right? Okay. And let's look at another subgroup of the same group. So let me just go ahead and erase and get a new board. All right. Now you can see this element here. This is an element of order 3. So the square of this element, you can verify that that will be this one. And this is the identity, the cube. So let's take this subgroup. Let's call it K as the identity 1, 3, 2, and 1, 2, 3. Now notice this, here we don't have to go ahead and check whether a left coset is equal to right coset or not. Okay, all that we can do is see this here. This is S3 has how many elements? Factorial 3, that is 6 elements. Here we got 3 elements, right? So the factor, I mean, calling it factor group, that's not fair. If we look at the set of left cosets, or that you also call index of K in G, that will be how much? 6 over 3, that is 2, right? So there will be only 2 left cosets and 2 right cosets. Now notice this, one of the left cosets is going to be the left coset by the identity element, which is this. So they will just be K, right? And the other left coset would be the elements that are by the elements that are not in there, right? So that will be by this, and those are bound to be equal because there are only 2 left cosets and only 2 right cosets, and one of them happens to be K, so they will be the same. So for the other one, it will have no choice but to become the same. So this subgroup, which remember this, that if you look at 1, 2, 3, that's an even transposition, right? 1, 3, 1, 2. Okay, then we call this group the alternating group, right? Or A3 on 3 symbols. So alternating group, which is a subgroup of S3, or AN in general, is a subgroup of Sn, and the index of this is 2. So that is AN is always a normal subgroup of Sn, all right? Now, so, the group of permutations, even though it's non-abelian, will always have a normal subgroup that is the alternating group. Now, fortunately, uh, I didn't have this facility when I took this course for the first time, close to 50 years ago. All right, but you have Sage Math, and there you can go ahead and check, in many cases whether whether a subgroup is a normal or not, just by a single command. So let's just go ahead and visit that facility. So let's take, say, permutation group on 5 symbols. Okay, so we are taking the symmetric group on 5 symbols. Okay, and after that, let's just take an element. And remember, how did you specify an element? You write the name of the group. Okay, and let's just take an element of order 5. That's kind of easy right now. So order 5 means the subgroup generated by A will have how many? 5 elements. All right. So let us define H by H as a subgroup generated by, not subgroup generated by this element A. Okay. And as you would expect, if you list H, we have 5 elements in here. Okay. So, and here you can ask Sage if this statement is correct. It will just tell you whether the statement of is true or false. And here, what is our parent group? S5. Okay, it tells us that a statement is false. That means this is not a normal subgroup of that symmetric group. Okay, now let us recall our quaternion groups. You can see all the subgroups are the identity plus minus 1, and the group with these 4 elements, and then another with these 4, and then with these 4, with K and the Hamiltonian group itself. Now any group is normal in itself because always the left cosets will be equal to right cosets. Now these 3 groups here, they are all of index 2, that is their sizes have half of the size of H. So these are all of sorry, they are all of order 4, okay, in a group of order 8, right? So the index is 2, and remember the way I showed you with the alternating group, what will happen is that the left cosets, every left coset has to be by an element, will have to be the right coset by the same element. And if we look at this one, plus minus 1, then these 2 elements, if you look at it, or if you look at them, rather, these elements, then these elements, they commute with, okay, plus and minus 1 commute with all the elements. Okay, so what will happen is that if you take a left coset or a right coset, elements will turn out to be the same. And remember, such a subgroup is also called the center of the group. Okay, but let's not go that much in detail, but you can see this here, that H is this group H is a non-abelian group. Okay, this is non-abelian, but still all these subgroups are normal. And we know if I have an abelian group, all the subgroups will be normal anyways. So what we are working on is this, that if G is a group, H is a normal subgroup of G, right? Okay, of G, then G over H, we call this factor group, right? And this is a group of left cosets of H, or you can even take it as right cosets of H. So this is a group and with the operation that xh times yh equals xyh. So we saw that if a group is abelian, all the subgroups are normal subgroups. Even if it's non-abelian, we saw that sometimes, like in quaternion groups, all the subgroups were normal subgroups. But let's just turn to uh, again, the interesting group Sn, where this is the permutation group on n symbols. So we know S2 is abelian on two symbols. It has order 2. So there is not much to talk about. So let's go to Sage Math and start looking at this, starting from S3. Okay. So let's take S3 as symmetric group of order 3. And now this program, Sage Math, it runs on top of Python. I don't know much programming in Python. And before that, there used to be a program called GAPS. It runs on the top of that as well. And actually, if you did this, if you involve gap here in the following manner, let me just bring this up here. See, I put S3. So what am I asking? Am I asking it to give us the normal subgroups of S3? And when I do that, it tells us that the normal subgroups are the group itself, the alternating group, which is always normal subgroup, and then the symmetric group, right? So that's all that we have for the normal subgroups of S3. Now let's go to S4, okay? And then we will look at, say, symmetric group 4. And then again, what we would do is bring, no, sorry about that. Okay. This is not what, let me just type it and that will be the best. Will give me some practice. Okay, so I want the normal subgroups, okay? And so let's list the normal subgroups. So what it gives us is that we have symmetric group, the group itself, then the alternating group, we know that will happen always, the trivial group, and then we got this guy here, the group generated by these elements, okay? So let's just go back and again look at this group and see how we can get the factor groups, or how we can have Sage Math compute the factor groups for us, okay? Now, so here, let's just pay attention to this group here, okay? And in this group, notice this, that I got 1, 4, 2, 3. If you square it, you will get the identity because order 2, right? And so the order of this will be 2 as well. Likewise, 1, 2, 3, 4. Even this square will be identity. And if you multiply these 4 elements, okay, 1, 2, 3, 4, you will get a third element. Why don't we use Sage Math to do all the calculations? Because now we know how to multiply permutations. Okay, so we'll just go ahead and have these calculations in Sage Math. Okay, so let's take an element, okay, of S4. So we got 1, 4, 2, 3, 2 disjoint cycles. Okay, So this is how we defined A. Let's define B by defining the other element 1, 3, comma 2, 4, and the product of disjoint cycles or transpositions. Okay, and now what we will do is we'll look at the group generated by these two elements. All right, so let us call K as, okay, a subgroup of S4, okay, that is generated by who? A and B, okay. So there we are. Now let's list the elements of K. How many elements does K have? These are these four elements, and which are actually, corresponding to the client's four group. So what we got is that we got a normal subgroup of four elements in S4, and S4 has how many elements? S4 has 24 elements. So when we look at the factor group of this, then what we shall see is, so G is S4 here, and then K is the client's group or a subgroup of order 4 in G, because we are looking at client's group as a group of permutations. So G factored by K, here I have factorial 4, that is 24 elements. So G factored by K will have how many? 6 elements. So there will be 6 cosets and they will form a group. But when we are going to ask Sage to give us those factor groups, what it will do is that it will give them to us as a subgroup of permutation group on 6 symbols. But anyways, I mean, that's how we have to recognize, and we can just go ahead and obtain them in other forms if we would like. So let's see how Sage Math will give us the factor group. Okay, so the way we shall obtain this in Sage Math is that we will just ask for instead of factor group, it will take it as quotient. So we want quotient of K in S4. So what it did was that it gave us the generators, which of course should give us 6 elements. Let's just define them. Okay, let's take S6 as a symmetric group on 6 symbols, and then we will define an element C in S6 as the this element. What is this? Well, these guys are these guys are the uh, these guys are the elements of what? This is an element of order 2. It's getting too late in the morning. That's okay. And then we are taking the other element, which is what? Which is of order 3. So here, okay, all right, close the quotes, okay. So there we go. And now what we would look for? We would look for the subgroup of S6, right? That is generated by C and D, and we should get a subgroup of 6 elements, right? And here it is, okay, subgroups. So we could do this actually. Let's just write H as this subgroup, okay. I think we could try to do that before also, could have tried to do that beforehand also. And if we list H, I think it will give us the 6 elements, which it did, the identity and the other 5 elements of the factor group. Okay, so we got them all. All right, okay, or actually, you may not see the whole thing because it's out of the, some of it is out of the recording area, but it is showing 6 elements, and I shall show it to you in some other calculations, okay? So now let's just examine the normal subgroups of S5. Okay, so let me just put S5 as this, and then we will say what, gap S5 dot normal subgroups. Okay, what it gives is, well, it gives us only 3. That is the symmetric group, the identity, and the alternating. Okay, so how about S6? What happens there? If we, no, sorry, one moment. Okay, let me just write it out. Something went bad there. Symmetric group. Okay, on 6, and then I will go gap S6 normal subgroups. Okay, and again we have the same thing, and so we can just keep on repeating this, right? Okay, so let's for instance go for S7. Okay, so here 7, and we would do this, change this to 7. Okay, I don't know which way it's faster. Okay, so there we are, and then we will bring these guys here. Okay, copy, and then here we have 7, delete, and again we get only 3. Okay, so let's make a big jump just to think that maybe how about this? Well, 7 was a prime. Let's take something like a which is not a prime. I mean, let's take something like 24. Okay, so here we have 24. So now you may make a conjecture, right? That is, looks like we can make a conjecture. I mean, I have seen this result, so let me not do any drama or acting here. Okay, that is, here what will happen is that all that you will get are just as you did in the other case, just the alternating group and identity and the group itself. So it appears that for n not equals 4, so between 3 and onwards, for n not equals 4, this is all that we will get. Okay, so we can discuss that later because it's just like we are looking at some examples here and just trying to make a conjecture, but that's not a proof. Okay, so now let's just go back to, sorry, I'm just going to make a crude drawing here. And so what I'm doing is this, that I'm going to remove the origin here. Okay, all right, and so this so I have removed the point 0. So what we got here is C star, the group of non-zero complex numbers. Now remember, this is the circle group S1, right? Okay, the group of all the elements that are on a circle or whose distance from the origin is 1. And remember this, you also saw that the cosets of this would be just elements like these, and so all the points just being on that concentric circle, and all these will be disjoints. So these were all what? Cosets, right? And if I multiply this coset with this coset, say these cosets, say I multiply, say this is R1 and this is R2, then what will happen is that it will just go on the circle with radius R1, R2. That's how that coset will behave. So I'm about to close it, so I hope I'm not going super fast for you. But what we are curious about is this, that it's good. I mean, the geometry makes sense, and then we can see that we can do computations with that, but we want to see, would it look like a well-formulated group G in any sense? So that's what we are going to get to the into the next presentations, which will be the homomorphism and the first isomorphism theorem. So, so I shall see you in the next presentation, and thanks for going through this one. All right, thank you.